Oh, I'm sorry about that. But thank you all for joining, and I would love to introduce our speaker today, Benedikt Bünz. He will be discussing cryptography for the cryptocurrencies. And so I would like to turn it over to you now, Benedikt.
Hello, yeah, thank you very much. Let me see what we can make this into full screen. Okay, I think that should work. So yeah, thank you very much. My name is Benedikt Bünz. I am a PhD student at Stanford University, and I'm also the head of research at Findora. And I will talk about what makes crypto and cryptocurrencies, so cryptography. And obviously that's a huge topic, and I'll only be able to touch on a couple of things, but I hope we get to explain at least the basic tools that are used in cryptocurrency today, and also dive in a little bit deeper into some of these topics. So what is a blockchain? Well, you can really think of blockchains as having multiple layers. So there's a consensus layer where people agree on, where nodes agree on the state of a ledger. You have some ledger, call this, part of the blockchain, and there's multiple participants that agree on the ledgers. And the key property is that we have the global decentralized blockchain where the entire world may want to agree on what the state of the ledger is, or you can also think of a much more local private blockchain where only a few participants agree on what the blockchain is. And above that is the sort of compute layer, which you can call a blockchain computer, where really the question is which kind of transactions are added to this ledger and what kind of things can you do on this ledger. So what smart contracts or what applications can you run on this? And then this sort of sits between layer 1 and 2. Layer 2 is really the smart contracts and so on. So you can use the blockchain to build different applications. You can even use the blockchain ledger to build additional ledgers on top. You can build tokens or whatever. And then the top layer is the user interface. And what we are going to talk about is the cryptography of cryptocurrencies, and that really sits in layer 1.5 and 2 here. It's the consensus layer needs some cryptography as well, but that is mostly limited. Most of the cryptography that we're talking about is really in this layer 1.5 and 2. And we tested this before. If you guys have any questions in between, please go ahead and ask them in the chat, and I'll try to answer them as I go along. So what are some of the core crypto primitives that we use? And it turns out that blockchains are really consumer of a lot of very cool and very advanced cryptography. And in fact, I would say it's the internet, is obviously one of the biggest consumers of cryptography. You need digital signatures and encryption to make the internet that we use today work. Like even this webinar would probably not work without, at the very least, digital signatures. But it turns out that cryptocurrencies are, there seems to be a good match between what we call more advanced cryptographic primitives and the needs that blockchains have. And this includes Merkle trees or Merkle commitments and succinct proofs, zero knowledge proofs or SNARKS, and also more advanced signature schemes. So that is why there's been also a lot of interest from the cryptography community, and I would say the advent of cryptocurrencies has really also spurred a lot of new developments and new directions in the academic space around cryptography. So the first thing we're going to start up is probably one of the most powerful cryptographic primitives, which are so-called digital signatures. So what is a digital signature? Well, if we look at a physical signature, the goal of a physical signature is to bind some transaction to an author. So I have a check here where Bob agrees to pay Alice $1, and then Bob signs this check. And the idea is that, you know, it's hard to, if Bob issued this check, then it's the signature is identifying. So it's easy to see that, in fact, it was Bob who issued the transaction. But the problem in both the physical world, but significantly more so also in the digital world, is that this doesn't actually provide a lot of binding, because anybody can copy Bob's signature from one document to another. So I could just take this check and write a second check where Bob agrees to pay Alice $100. And still, you know, especially if we're in a digital world, I can literally just copy and paste the signature, which is exactly what I did here. I literally just copied and pasted it, and now I have a different statement, and it's not clear which of these statements Bob actually issued. So in a digital world, this sort of signature, this timestamp, wouldn't have much meaning. So we need something different. We need something where the signature is dependent on the document, so that a signature is only valid for a given document and cannot be transferred to a separate document. So how does this work? Well, we have a so-called signing key, SKs, the secret signing key, which Bob has access to, but only Bob has access to. And then it uses a signing algorithm which takes as input the message that Bob wants to sign. So here Bob wants to sign the statement that he agrees to pay Alice $1, and then he produces his signature. And Alice, or someone else who wants to, a bank maybe, who wants to make sure that this check is correct, will act as a verifier and use a public verification key. So the secret signing key and the public verification key are linked together. The secret signing key only Bob has access to, but the public verification key everyone has access to. And then I can use the signature and the document and the public verification key to see whether the signature is correct. So I will, in the end, just output accept or reject as the verifier. And to maybe make this a little bit more formal, what we do is we have the first thing we do is we have a so-called a gen algorithm, where the algorithm outputs a key pair, the secret key and the public key. And then using the secret key and the message, I can output a signature. And then using the message, the public key, and the signature, the verifier can output accept or reject. And the security statement, or the security of signatures, is that even after I've seen many signatures by Bob in this case on many different messages, even if, you know, the adversary gets you to sign a very specific statement, you know, he gets to sign, he makes you sign that Bob wants to pay Alice $1, you can never forge a signature on a new message. So even if I know a signature on where Bob says I want to pay Alice $1, I cannot possibly create a signature on message where Bob wants to pay Alice $2 or even $1.5. And that is the security property of these signatures. And these signatures are not only used in, I'm sure you can imagine how they are useful in financial transactions, but this is in fact what is used in the internet whenever you visit a website and you get the little I think green lock or whatever they use today. So in SSL, in HTTPS. And what does this mean? Well, it means that if you're visiting google.com, it means that Google has issued a signature that, in fact, this is the correct website that they wanted to send you. So they will produce the website google.com, and then they will sign it to make to convince you that this is in fact the website that they wanted you to visit. And then once you receive it, you're sure that no one in the middle, even if there was someone in the middle that transported the website to you, some internet provider, that no one was able to change the website while keeping the signature valid. There are different families of signature schemes. So on the internet, it's still a lot of RSA signatures, which have the downside that the signatures are fairly large, but advantage that they're fast to verify. And then there's these discrete log signatures, which are used in Bitcoin and Ethereum today, I think, for the most part, which are very short. And then there's something sort of the newest kind of signatures are BLS signatures, which are the B in BLS signature stands for Dan Benet, who's my advisor, and these have some additional properties, which we will talk about in a second. And one core issue with cryptography in general that you may have heard about is that a lot of the current cryptography that we use is susceptible to attacks by a so-called quantum computer. Quantum computers don't exist yet, but in they might be around in 30, 40, 50 years. Nobody really knows. But there's a lot of effort going on into developing signatures which are secure against quantum computers. And we have these signature schemes, but unfortunately, the reason why we don't use them currently is because they come with a significant efficiency loss. So they would be significantly larger. So how are they signature used in on the blockchain? Well, they're really used everywhere. They're kind of the key building block. So the one core thing is, if I want to issue a transaction, I need to make sure that it's properly authorized, so that I was really the one that I wanted to issue the transaction. But also in consensus things, if different miners want to say which block they approve, which block they don't approve on, they can use signatures there. And also in larger scale governance votes, if different organizations want to change the blockchain in different ways, then they can also use signatures there. So here, for example, here we have these transactions which Alice and Bob send to the blockchain. They sign their transaction, and then the miners can verify all of these transactions. So what you can see here is that every single transaction has an individual signature. And this is where BLS signature aggregation comes in. And the cool property of BLS signature aggregation is that I can take multiple signatures and compress them into a single signature. So what does this mean? Well, I have 3 different signatures by 3 different participants, and then I can use an aggregation algorithm, and anybody can really run this aggregation algorithm to produce 6 star, such that 6 star is valid if and only if all of the individual signatures are valid. So to verify this, I still need to have all of the public keys and all of the transactions, but now I only need a single individual transaction, single individual signature. So this is significantly smaller and is a huge space saving. And there's no need to store the list of signatures on the blockchain anymore. And so, for example, you might have a miner who assembles a block and then uses all of the signatures to the signature aggregation to create a single block. And the most advanced signature schemes like BLS, or in particular, I think BLS is the main one that we know that has this property, can be used to do signature aggregation. The next thing that I want to talk about is so-called Merkle commitments or Merkle trees. And by the way, if there are any questions on signatures at this point, it might be a good time to ask. Is there audio?
Hi, Benedikt. Looks like we're having some issues with the audio.
It says better audio now.
Yeah, it kind of comes and goes. Somebody suggested to maybe turn off the webcam to get better, more bandwidth.
Okay, I will. I'm going to shut the. I see the. It's okay. Does the audio seem better?
Yes, it seems better to me.
Okay. Well, I'm sorry about that. I hope that it will be better from now on. Are there any?
Looks like you do have a question.
Question here. Generally, we speak about making public keys available. The Bitcoin paper speaks about keeping public keys anonymous. The Bitcoin addresses, however, linked to the public key. There's a good question. So I will talk a little bit later about privacy and whether to make your public key anonymous. But a public key, so the question is, whether we want to keep these public key private or anonymous, and I think how it relates to privacy. And I think the answer to that is that certainly it really depends, because it depends whether the public key is linked to an identity. So is it linked to your real name, or is it just some arbitrary public key? And if we look back at the very beginning, it turns out that the generation algorithm is extremely cheap. So I can always create new public keys, and I can create many different public keys, and there's really no cost to it. And if with every transaction I create a new public key, then there's no linking between it's harder to link the public key to a real world identity. But what Bitcoin does, or what a lot of these blockchains do, is the transaction will not necessarily, or the blockchain the blockchain address is not a public key. So whatever your Bitcoin address is not a public key, but it is the so-called hash of a public key. But this is really just a technicality, because once you issue a transaction, you have to reveal your public key such that someone can verify the signature. Okay, audio seems pretty clear to me. Could you please talk about pure incompleteness? And I won't really, that's not the topic of this. If someone wants to change the blockchain. I mean, in general, blockchains are append-only ledgers where things are only added. Okay, so there were a couple questions. Thank you for them, and I'll periodically try to look at them. But we'll go on now and talk about the next topic, which is Merkle commitments and Merkle trees. So what is a commitment? Well, a cryptographic commitment emulates an envelope. So what I can do is I can write down some data and imagine I can put it into an envelope, and then I can send this to a verifier. So again, our friends Bob and Alice here. So Bob sealed some data in an envelope, sends it to Alice. Alice cannot see the data, But she knows that once Bob committed to the data, he cannot open it to anything but what he previously committed to. Then later on, Bob can reveal the data, and Alice can verify that the data was committed to correctly. So this has many applications. So for example, think of an auction where every participant commits to a bid, and then once all of the bids are in, everyone opens their commitment. Or a very classical example is rock, paper, scissors, or I play some rock, paper, scissors over the phone. And what I can use is I can use a cryptographic commitment to commit to what I'm going to say, and then after that open the commitment to reveal what I meant, such that the problem with playing rock, paper, scissors over the phone, not sure whether you've ever tried it, but it's if one person goes first, it's very easy to win for the other person. So a little bit more formally, a cryptographic commitment has two algorithms: a commit algorithm, which takes in the data and outputs the commitment, which is public, and some opening key or opening information. And the verification algorithm takes the data, the commitment, and the open, and outputs accept if in fact commit was a valid commitment to data. And the security property is that Bob cannot produce two valid openings to a single. He cannot open the same commitment to two different things. So if I committed to data, I cannot open it to data prime. If I committed to rock, I cannot open it to paper. And it's also hiding in that the commitment reveals nothing about the committed data. So you cannot see from the commitment whether this is a commitment to paper or scissors. So what sometimes commitments have also, some commitments also have a different property, which is that they're shrinking. So say I want to commit to a tuple of values, so here 8 different values, then I can create a succinct commitment. So the commitment is a constant size, so say 32 bytes, even if I have millions of elements that I commit to, and still the binding property holds. So still I can only open it to the entire tuple. And it additionally has a second property, which is that I can also show you that here x4 is the 4th element in the commitment. So I commit to 8 things, and I can show you that I can open it to only show you that the 4th thing had some value. And this is also called a vector commitment, because I'm committing to a vector of things. So how do we do that? Well, the key way to do that is called a Merkle tree. This is invented by Ralph Merkle in the late 80s. And what we do is we use a hash function. So h here is, let me see whether I can draw. So this h here is a hash function which maps from, this is not going to go well when. So the hash function maps from a large string, so say from 2 elements, to something smaller. So I take in, two 32 byte, or I take in 64 bytes, and I output something which is only 32 bytes. But it has the property that if I hash x1 and x2, I won't be able to open it to anything else but x1 and x2. So the hash function itself is a commitment. So what I do then is I create if I wanted to commit to all of the data, I could just hash it and give you the hash of the data. But this wouldn't have this property that I can open it to a single value. So what I do is I build a tree. So I always take 2 elements, and then here 2 elements, hash them together to get a new element. Do that over here with x3 and x4 as well, and then take the outputs, hash them together, and so on and so forth. So this gives me a tree. And then if I want to show to you that x4 is part of the tree, well, how can I do that? Well, it turns out that I just need to look at the path from x4 to the so-called root of the tree and give you the elements that are on the path. So I give you x3, y1, and y6. And then if you want to check that x4 is indeed part of this tree, well, then I just take x3, and x4, hash them together, check whether I get y2, or compute y2, take y2 and y1, hash them together, and then I get y5, hash y5 and y6, and in the end I get this final root. And if this is correct, then if this is the final root of the Merkle tree which I expected, then I know that x4 must have been part of the tree. And why did we do this? Well, the nice thing is that the size of the proof is only linear in the height of the tree. So the height of the tree, whereas the number of data that I'm storing is linear in the width of the tree. But if you think about it, if I commit to a set of s things, then the height of the tree is only logarithmic in the height, is only logarithmic in the size of the set. So if I commit to 8 things, then the height is only 3. But if I commit to 1,000,000 things, then the height will only be 20. So this goes really, really slowly and makes these opening proofs very efficient. So these Merkle trees are also used all over the place. For example, one way that they're used is that all of the transactions are in a block are committed to in a Merkle tree. So if I have the so-called block header, then I will be able to show to you that a certain transaction was part of this block. So say David sent to Carol 3 ether, then I can give you a very efficient proof that in fact this transaction here happened in this block. And you can check that this one transaction which I care about, I might not care about any of the other transactions, but you can verify that this was in fact included in this block. And exactly, so this is the use case. And so again, for 1,000 transactions, the proof is only 10 hashes. So significantly faster. Another very interesting application is keeping the state of the blockchain sort of off-chain. So again, say I know, I have my blockchain is it's really a ledger of accounts and balances. So I have a bunch of users, and each of them has some balance on the blockchain. And then I want to create a transaction where Alice wants to, well, or say first that Alice wants to prove that she in fact has 10, let's say, ether on this blockchain. Well, then she can prove to anyone who has this Merkle tree hash, they only need to store a single hash. She can prove to anyone that in fact she is part of this hash, and that in fact she has 10 coins. And she can do this very efficiently. And another interesting thing is that now I can even create transactions. So say Alice wants to send 3 Bitcoin to 3 ether to Carol. Well, then she needs to prove that in fact she did have 3 ether. So what she will do is she will create a transaction, and as part of that transaction, she will send her a proof that her previous state was in fact that she had 10 ether. So anyone can now verify the transaction very locally without having access to the entire database of account balances, because they just get this proof that Alice's part of the database was in fact that she had 10 ether. So here's this example. Alice sends to Bob 2 Bitcoin, and then she gives proofs that these things are correct. And it turns out these Merkle trees commitments, they even have additional properties where you can also update them very locally. So you can update the balances locally, and then create a new commitment to the new updates. So yeah, so what this would do, it would really create so-called lightweight miners, where these miners don't even need to store the entire database anymore, the entire ledger. They just need to store a Merkle tree root of the entire database. So this is the end of the Merkle tree section. Let me look at some questions here. We will talk about zero knowledge proofs. Do we need an infinite loop mining protocol to prevent the quantum computer from mining? No, and in fact, it turns out that quantum computers really don't have anything to do. They really won't change the way that mining works. So quantum computers aren't infinitely more powerful than regular computers. That is not how quantum computers work. It just turns out that they can do some very specific operations significantly faster than a classical computer. So the usual example that is used is factoring. So any number, so say 15, can be written as the product of prime factors. So 15 is equal to 3 times 5, or 21 is equal to 7 times 3. And for very large numbers, it's quite hard to find the prime factors of a number. But for a quantum computer, this is easy. And in cryptography, we usually rely on, or we always rely on certain problems being hard. So a lot of our cryptographic algorithms, such as RSA signatures, rely on exactly these problems, which are hard for a classical computer, but easy for a quantum computer. But it turns out that things like, there's other cryptographic things like Merkle trees, which are not affected at all by quantum computers. So your Merkle tree is going to be just fine, and your mining is going to be just fine. Next question by Dennis. Hi, when you send signed messages to the blockchain, how long does the message stay there for before it times out? So this is really orthogonal. So the question is, if I send a message to a blockchain, how long, does it stay there? This is really orthogonal to kind of what we're talking about today. What happens is that it depends on the specific blockchain and the specific network. What happens is that if I can send a message, and then the miners or validators of the blockchain can choose to add it to the blockchain, or they cannot. And there's not really anything like a timeout. And once it's added to the blockchain, it just gets added to the ledger, and it stays there forever. How can I use a chain to create a token belonging to an ecosystem? I don't think this is really related to what we are using. Could we tell something about MD5 and SHA-256 too? So MD5 and SHA-256 are just two different hash algorithms. So here I used, in this example here, I used the hash function. And you can implement this with different hash functions. One of them, probably the one that you should use in general, is SHA-256, because it's considered to be the most secure. And MD5 is also a hash function in that it maps two things to a single thing, but it's not considered to be secure, which means that a computer that, a very, very powerful computer, can hash x1 and x2 and get y1, but he could find x1 prime and x2 prime, which also hash to y1. This is called a collision. So this is not, and then this Merkle tree doesn't have the properties that we want, where I can really convince you that something is part of the Merkle tree, because I could have come up just with different values that we're committed here. even though each prover has to only supply a proof size of log s, doesn't the system have to store all hashes, leaves, non-leaves, and nodes, which is s hashes? So the system in total might have to still store all hashes and all nodes, but the interesting property is that everybody can just store what they care about personally. So if I only care about x1 and x3, then I can only store these things. And also this is very advantageous for, say, a mobile client, which might not want to store everything. So this is really about outsourcing and load distribution, where I can distribute part of I can store part of the tree on one server, part of the tree on another server, and maybe mobile clients don't have to store anything. Couldn't Alice have two transactions and use the prior transaction in the proof? Hasn't and double spent. As you talk about quantum computers, where do you see the challenges to be addressed by blockchains in terms of quantum computers, and when? I think I'll leave that question to the end to talk about quantum computers a little bit more. So, because I want to talk about another very exciting topic, which is proof systems. So, what is a proof system? Well, say I have some public program. You can just think of this as some short code, which takes in some public input x and some private input w, and the program will restrict it to output only 0 or 1. This seems like a very strict restriction, but it turns out that you can write most programs in this way. And then the goal is that I, as a prover, want to show you that I know a w such that for this public input x, this program outputs 1. And what I will do is that I will be able to send you a proof. We have some public parameters here as well, but in general, I will just be able to send you a proof. And then the verifier takes as input just x and the proof and outputs accept or reject. And the key properties, this has multiple key properties, which is that, if I'm in fact know w, then I can always convince the verifier. This is called completeness. So I can create a valid proof. And in fact, the first thing is very easy to satisfy because I could just send you w, right? There's no way to this is very easy. The second property is soundness, which says that if I don't know a w, then I cannot, then the verifier will reject with high probability. And in particular, if there is no such w, then the verifier will, and with high probability here means really all but the probability that I can convince a verifier without knowing a w is like winning the lottery 1,000,000 times in a row. And then there's this very exciting third property, which is called zero knowledge, which says that the proof reveals no information whatsoever about w. And we will talk about that. And then there's the fourth property, which also is very exciting, which is about succinctness. So this is called, if I have a succinct proof, they're called a SNARK. And there the idea is that the proof is significantly shorter than w. So say w can be really, really large, but the proof is just, again, logarithmic in w, and the verification time should also be equally fast. And sometimes I have both of these properties together, and then I have something called a zk snark, so a zero knowledge snark. So what is the application of this? And this is, by the way, you should be sort of surprised that, I mean, maybe you've heard of these things before, but both of these properties are highly, highly non-trivial, right? I can prove to you the zero knowledge property means that I can prove to you that something is true, right? I can prove to you that some arbitrary code is, accepts, goes to 1, without giving you any information about why it's true. So I can, and the second property means that I can convince you of something really, really complicated. Like we'll see some cool examples for this. And you have to work significantly less than convincing yourself. So this is, yeah. So what are the applications for this? Well, the first application is we're going to use the succinctness property, and we're going to use it for scalability. So normally I have in the blockchain system, every miner or every validator needs to verify every single posted transaction. So this really becomes a bottleneck and leads to sort of limited scalability, and the fact that, say on the Ethereum blockchain, the smart contracts that I can run, someone has estimated that the whole Ethereum blockchain computer is about as powerful as like a computer from like the 1980s or something. So really, really weak. Like every single phone is currently more powerful than the entire blockchain computer. So how can we use SNARKS and the key problem is exactly this, that every single miner needs to verify every single transaction. So what I can do to alleviate some of this is that I have something called a roll-up server, where all of these transactions get sent to the rollup server, and then the rollup server produces a succinct proof, a snark, which asserts that all of these transactions are valid. And then it sends a summary of all of these transactions, so kind of, the final balance is, maybe Alice and Bob sent each other a bunch of money, or a bunch of money gets moved around, and the rollup server will do all of these transactions and just in the end send a short summary of all of them, and then give a short proof that all of them were done correctly. And the miners now just need to verify this proof. But if you recall, the key property of the proof is that verifying this was significantly easier than verifying all of the individual transactions. So the statement that I'm proving to you is that I know kind of a bunch of transactions and that all of them are valid here. And you now need to do, for say, just to give you an example, like say there's 1 million transactions that happened. Now the miners just need to do work that is roughly proportional to verifying 20 transactions. Or for 1 billion, it's 30 transactions. So again, we have logarithmic scaling. And in fact, you can drive this there's sort of even more extreme versions of it, where I give you the entire blockchain, right? Now why don't you send everything to the rollup server? And in fact, you can kind of do that. I can give you an entire blockchain and then a short proof that the entire blockchain only contains valid transactions. So you don't need to go through all of the transactions in the blockchain anymore. You can just verify this one final proof, which also is, they are like 200 bytes in size. So the second application is something where we use privacy. So the problem is that all of the data, we already talked a little bit about privacy, but right now, today, all of the data on the blockchain is public. And this means all of the transactions are public. And this is actually really terrible for businesses, because say I want to, say I'm Ford or whatever, and I want to buy some tires from Goodyear and do blockchain transactions, then everybody else, and especially my competitors, are able to see exactly how much I'm paying for these tires. And this is problematic, because I don't want to reveal these important business secrets of how much exactly I'm paying for it. And a different approach to this is to say that instead of revealing the data publicly on the blockchain, I'm using a tool that we already talked about, namely hiding commitments. So I will only have commitments to this data on the blockchain. And then if I want to change the data, I will give you a zero knowledge proof that in fact this data was changed correctly. So I now have I had my first state, and now I have a transaction which updates the state, and I will give you a proof, and everybody can verify that the update to the state was correctly, but still only it is hiding, so only the people that are allowed to see it are able to see the update to the state. So the zero knowledge proof will assert that the state transition from state I to state I plus 1 is correct with respect to the, say to the decentralized application. And so one very simple example of this is just say I want to send money. Now, right now in a Bitcoin transaction, all of the amounts are public. So I can see exactly how much money is being sent from one address to another address. And we talked a little bit about linking to identities. It turns out that actually, at least in Bitcoin, it is fairly easy to link an address to a real world identity. So I can figure out, if I just receive money from you, then I can figure out what your addresses are, and I can link different addresses that you have together. So what you could do is, if you want to at least hide how much money you're sending, you could commit to, instead of having the clear amounts, so this is just an example of what is on the slide here, you could commit to the amounts that are being sent, and then I give you a zero knowledge proof that in fact this transaction is valid, so that no new money is created in this transaction, so that the money that went into the transaction is exactly equal to the amount the money that came out of the transaction. So if Alice, if we subtracted 2 ether from Alice's transaction, then we'll add exactly 2 ether and not more to Bob's account. And but with the zero knowledge proof, everybody can just see that the transaction is valid, but only Alice and Bob are able to learn that, in fact, yes, their balances got updated, and no one else will be able to see that. So there's different types of SNARKs, which is some of them have something called, maybe you've already heard of this, but some SNARKs have a so-called trusted setup. So there's a setup thing where these so-called public parameters are created. And some SNARKs have this property that if the setup that uses some secret values, and if the setup is compromised, then the prover can break math. So it can prove to you that 2 + 2 = 5, or that a transaction is valid when in fact it wasn't really valid. And this is highly problematic, of course, because you need to, say I can prove to you that a state transition was valid when in fact it wasn't. I can prove to you that, here this transaction didn't create any money out of thin air when in fact it did. And the so Zcash used a trusted setup. So what did they do to alleviate this risk? Well, they had the setup be done by multiple parties, such that that all of these parties together would have to collude to actually learn the secret values that are being used in the setup. And the very most efficient SNARKs today are using a setup, but there's been a ton of research in recent years, and myself and others have also worked on this with proof systems like bulletproofs or supersonic, such that modern SNARKs do not really use the most modern and the most advanced SNARKs do not require a trusted setup anymore. And a big question today that I think, where's the research heading on this? And the big question today, I think, that people are working on is how much overhead is there for generating the proof? How expensive is it for generating the proof? So we have very, very small proofs. We have proofs without trusted setup. We have proofs where the verifier is extremely efficient. But currently, I think the bottleneck is the prover time. And that's what a lot of really interesting and cool research is going in. So what time is it? I have some, I guess now is maybe I have some more slides on optional things, but I think maybe if there's more questions, then now would be a good time. So I guess I can talk about the quantum computers question. So the question is, as you talk about quantum computers, where do you see the challenges to be addressed by blockchains in terms of quantum computing, and when? So again, quantum computers, the main challenges with quantum computers is they break some of the cryptography that is used today in blockchains. I mean, my honest answer is that if quantum computers appeared tomorrow, then we would have significantly bigger problems than blockchains, mainly that our entire internet and our entire financial system relies on cryptography, which is currently not quantum resistant. And I think that certainly, though, I don't think that quantum computers are around the corner. You know, sometimes you will read newspaper articles like Google saying they've done some, you know, they factored the number 15 into 5 times 3, but really we're very, very far away of especially building quantum computers that have the precision to solve cryptographic problems, because I'm not an expert in quantum computers myself, but one of the key problems with them is that so even in the classical computers, you sometimes have a so-called bit flip. So a bit flips from 0 to 1, and this happens, you know, maybe once in a trillion operations, and you can use so-called error correcting techniques to handle these bit flips. The problem is in quantum computers, this happens maybe like 1% of the time. So 1 in 100 times you have some quantum qubit flip, or the qubit isn't in the state anymore that it was supposed to be in. And this seems to be fairly inherent. And the problem is that currently we don't know how to solve these things. And this is less of an application quantum computers can be used for applications like optimizations, or, you know, people have touted for AI, or one really, really exciting applications of quantum computers is just modeling chemical processes themselves. And there, these bit flips aren't, as far as I understand, they aren't as important. But for breaking cryptography, you know, you need really sort of a precise quantum computer. And from what the experts say, it seems like quantum computers are always like, you know, at whatever time you ask, they're exactly 30 years away. So, you know, we have some seems like we have some time, but obviously the problem is no one knows, right? You know, no one knew when the pandemic was going to come, and no one knows when the quantum computer can come. So I think the current state is that we should invest a lot of research and a lot of effort, and this is being done, into cryptography, which is quantum secure against quantum computers, but we shouldn't have to worry about it quite yet. So is there a trade-off between prover and verifier efficiency? Interestingly, not really. We can get very, very efficient verifier efficiency, a very good verifier efficiency. There's somewhat of a trade-off between prover efficiency and proof sizes. So some of the most efficient proof systems have fairly large proof sizes. So proof sizes in the hundreds of kilobytes or tens of kilobytes, versus, you know, smaller proofs have maybe slightly more expensive provers. But there's no inherent trade-off here. So maybe we just need to work harder to find better proof systems. Okay. I have 5 more minutes. I actually want to go into maybe I'll try to go through a very cool example. I wanted to give you an example of, I talked about these zero knowledge proofs, but I wanted to give you an example of how the hell these things actually work, right? So one thing that I can do with the zero knowledge proof is a kind of fun example is that I can prove to you that I know the solution to a Sudoku without giving you any information about why this, what the solution of the Sudoku is. So you will be convinced that I've solved this Sudoku, but you will have no idea what the solution is unless you solve it yourself. All you learn is that there in fact exists a solution. So, I actually did this and solved the Sudoku. So this is not zero knowledge here. You can see the solution. But I want to show to you how can I prove to you that I know the solution without giving away any information. And the way that I do this is, so the first step is that I will write down a so-called permutation. So I'll take the numbers, right? Everyone knows how, I hope everyone knows how Sudoku works, right? The key property is that in each row, in each column, in each box, the numbers 1 to 9 should appear exactly once. What I will do is I will take a so-called permutation. So I'll take the numbers 1 through 9 and shuffle them up to, map every number to another number. So 1 maps to 5, 3 maps to 7, 5 maps to 3. And then I can use these new numbers to write down my Sudoku again. But now I replace every one with a 5, every 2 with 6. And it turns out that obviously if the first Sudoku is valid, then if the first solution is valid, then in the second Sudoku is also valid. Right? The numbers don't really have an inherent meaning. I have to swap them around. So how do I prove to you that a Sudoku is valid? Well, the first thing that Alice will do is she will shuffle up the numbers, and then she will write down the numbers and the Sudoku itself now shuffled, so the new numbers filled in. And she will use a commitment. You can think of this as, again, it's an envelope or a piece of paper to cover the Sudoku. And then the verifier, so Bob here, gets to ask a question. And he asked, show me row 4. So then what Alice does is she cuts out row 4 and shows that row 4 contains indeed numbers 1 through 9. Now Bob can verify that, oh yes, indeed, row 4 has number 9, but he doesn't actually learn anything about the Sudoku. Why? Well, because Alice first used this permutation to shuffle up the numbers. So this really could be any different combination of 1 through 9. All that Bob sees is that here, in fact, the numbers 1 through 9 appear. And he can do this different question like open column 2 or open box 1, and here all he will see is the numbers 1 through 9, and he can verify this. And the final question that he can ask is, oh, show me that you use the, so the more he does it, the more confidence he will get that Alice in fact has a solution to a Sudoku. But he also needs to know that Alice used the right Sudoku. So what he will do is he will sometimes ask, show me that you used the right puzzle. So then Alice cuts out the red squares, right? The red squares define the puzzle and shows the permutation. So the numbers, what the numbers 1 through 9 are mapped to. And then Bob gets to see, oh, okay, this is exactly the right puzzle that Alice has used. So the idea is that in every iteration of this protocol, Bob gets to ask a random question. And if Alice, in fact, has a solution to the Sudoku, then she will be able to answer all of these questions honestly, right? She can, show a row, show a column, show a box, or show the original. But if she was cheating, then it turns out that at least one row and one column and one box must be incorrect, right? At least one of them she must have cheated in. And what this means is that with probability, if she's cheating, then the probability that she will convince Bob is at most 8/9, right? You know, maybe in 8 rows she in fact has the numbers 1 through 9, but then in the 9th row she doesn't have the number 9 anymore. She doesn't, you know, the 9th row is not correct. So with probability 1/9, we will catch her. So the probability of her success is exactly the inverse of that, 8/9. So what I can do is now, you know, 8/9, that's still, she has an 88% chance of succeeding. So this is not very good. But what I can do is I can just repeat the protocol over and over again to get more and more confidence. And with every single different question that Bob asks, he will get more and more confidence that Alice in fact knows an answer. So after one try, the probability that Alice can cheat and succeed is 88%. After 2 tries, it's still 79%. After 10 tries, it's only 30%. But after 1,000 tries, the probability is so small. It's like this is like winning the lottery probably like 100 times in a row. So this just won't happen. This after 1,000 tries. This is 1 in a billion, trillion, quintillion. You know, a huge number. So very, sorry, not a huge number, but a very small number. But obviously, so what is the problem with this approach? Well, the problem is that if I get to ask different questions every time, then I will learn if I first in the first round ask, give me row 1, and then give me row 2, and so on and so forth, then slowly over time I will actually learn the solution, or Bob will learn the solution. So this doesn't quite work. Well, but what can we do? Well, what we can do is that in every round, Alice can use a new permutation, so she can shuffle up the numbers again. So why does this help? Well, this means that what corresponded to the number 6 in the first round now might be something completely different in the second round. So 6 could be 3, or 9 could be 4. So there's no correlation whatsoever in any of the single rounds. So Bob really learns no information whatsoever by just opening a single row in a column. All he sees is that the numbers 1 through 9 are up here. So this is why the protocol is zero knowledge. So here, you know, we open row 1 and then open box 2, and the 6 that we see here in row 1 and the 6 that we see in box 2, they might be related or they might be completely different. There's really no saying. So yeah, that was just an example of how zero knowledge works. And I think we're now a little bit over time. There's one more question which I want to answer, which is Zcash is one example of ZKP in production. But what timeline do you see that we will do you foresee that we will see more widespread adoption of ZKP in production DLT use cases? That is a very good case. I mean, Monero is another example that uses zero knowledge proofs, and on the Ethereum blockchains, there's now apps like, I think Rollup is actually already deployed that uses zero knowledge proofs. So I think this is happening very soon. And in fact, at Findora, we're working on exactly that. You know, we're trying to build sort of a ledger system for financial applications, which uses a lot of zero knowledge proof. And I think the idea is that, especially financial applications, like say I have a hedge fund, I don't want to, I have what cryptography and zero knowledge proofs are really good at is showing to you that some rules are followed without revealing to you any unnecessary information. So for example, as a fund, I might want to show to you that my fund follows a certain risk profile or follows some regulations without revealing any information about what I actually invested in. But I might want to say, I only invested in, say, whitelisted companies. And then I can use a zero knowledge proof to show you exactly that. You know, I can show you that my portfolio is only whitelisted companies, or it has a certain risk profile, but I won't reveal anything else for it. So it is a really great leverage. It really does a good job. Zero knowledge proofs do a great job at balancing privacy and auditability. And I think that is where a lot of the really exciting applications of zero knowledge proofs in production are happening. And so I foresee zero knowledge proofs as something that is, you know, coming now and soon, and will be certainly on the rise in a lot of different blockchain and DLT applications, and even beyond that, to be honest. So where do I
Okay.
send my private questions? That I don't know. Okay.
Hi,
I think
Benedikt.
that's it.
Yeah, if you don't mind, could you please put your contact, your email, just in case we have any additional questions, in the chat for everyone?
Yeah. So it's just benedikt@findora.org.
Okay.
I just put it in the chat. So if you have private questions, go ahead, send me an email. I'm fairly busy, so it might take some time to respond, but usually I respond eventually. So
Okay.
please go ahead and send me a question. Yeah.
Oh, all right. Well, thank you so much for joining us. It's a great topic, great presentation, and thank you for all the attendees that joined us as well. If there are any questions, feel free to reach out to Benedikt. He put his email address in the chat, or you can follow him on Twitter or other avenues. If you have any questions as far as EEA, feel free to send us an email as well. But I think we will wrap it up right here. So I hope you all have a great day, and we'll see you at the next education series.
Okay, thank you very much. Bye.
Thank you. Have a good day.